Hello, welcome to a review of solving polynomial and rational equations. So we know an equation is just a mathematical sentence stating that two expressions are equal to one another. But what is it that makes the equation a polynomial equation? Now we see these in lots of different forms, but basically what you're looking at is for all of the terms or the components of that equation to be of a specific form, and I'm going to call it k times x to the nth power. So all the pieces of your equation should look like that, where k is just some real number, so you can have any real number coefficient, and then n, our exponent, represents a positive integer, like 1 or 2 or 3 or 4. So you're looking for terms in your equation that look like that, so like 3x squared or 2x to the first or x cubed. Any combination of those being added or subtracted means you're looking at a polynomial. So you won't see any absolute values or radicals or fractions with x's in the denominator, just those specific types of terms. Okay, so when you're looking at a polynomial equation, it's important to distinguish between the degrees, and I'm going to classify some by name here, but it's the degree that's important because it's going to dictate how many solutions that polynomial equation has. So for example, if your polynomial equation has a degree of 1, meaning the largest exponent you see on an x is a 1, that's what we call a linear polynomial or a linear equation. If we have a degree of 2, we're going to call that a quadratic. If we have a degree of 3, we're going to call that a cubic. Degree of 4 would be quartic, and then you have quintic, and it just keeps going because that exponent, remember, could be any positive integer. But we're going to focus on a review of just, well, mostly quadratic, but linear equations we should be able to solve at this point too. So if you're going to solve a linear equation, again, that means the degree is 1. That means you're solving for 1x to the first. You're looking for just one solution. Again, that's why the degree is going to be important for us. It tells us how many solutions we're going to be looking for. So a quadratic equation, a degree of 2, should have 2 solutions. Or a cubic equation, a degree of 3, should have 3 solutions. Now, if we're going to solve a linear equation, if we're just going to look for one solution, we're just going to get the 1x to the first by itself in that equation. So, typical solving strategies, getting x by itself using inverse operations. Now, if we're going to solve a quadratic, which will be a big focus for the first part of our lesson, we have lots of techniques there. It's possible, just like a linear equation where we isolate x, to isolate the x squared, and then we do the inverse of squaring, which is taking the square root to both sides. It's possible that we can factor. It's possible that we have to use the quadratic formula. So we have lots of options there, and we'll go through examples for each of those. And then as the degree increases, the strategies are very similar to quadratics, minus we might not have a formula. So in the same way we could isolate an x squared and then take the square root, we can isolate an x cubed and then take a cube root, and we can factor. So here, for instance, in the same way I can, for this equation, subtract 1 and for this equation, I could just subtract 1 and then divide 2. For this equation, I can get this x squared by itself by just adding over the 27 and then dividing the 3. Or here, I can get x cubed by itself by just adding over the 8, and then I can get rid of the cube by taking the cube root, right? Or add the 27, divide the 3, and then get rid of the square by taking the square root. So all three of these are polynomial equations that we can solve using isolation techniques, inverse operations. Now, it's not always possible, so again, we're going to do some review of mostly quadratic equations, but the strategies that we'll use there, some of them could be applied to higher degrees as well. So let's go ahead and practice, and this is all stuff that should be familiar, so hopefully this will be good. Alright, for example, in this first equation, the only exponent I see on x is a 1, so I know it's a linear equation. I'm just trying to solve for my 1x to the first, find my one solution. And so I need to clean this equation up before I can actually solve. So on this side, I don't have anything to do to simplify, but on the right side of the equation, I can simplify for sure. So I'm going to distribute the 2, giving me 2x plus 2. And then I can combine these like terms here. So I'm going to have a 3x minus 5 equal to, let's see, 2 minus 4x's would be negative 2x's on that side. And now, again, I'm trying to solve for my 1x, get my 1x alone, but I have x's on both sides. So I need to fix that. I'm going to go ahead and add 2x to both sides to combine those like terms. And then that's going to give me 2 and 3 makes 5x. So 5x minus 5 equal to 2. And now I'm actually at the point where I'm ready to solve and use inverse operations. So let me go ahead and add 5 to both sides. That's going to give me 5x now. I'm running out of space. 5x equal to the 2 and 5 makes 7. And then to get rid of the times 5 here, we'll divide both sides by 5. And then we're good. So x is going to be equal to exactly 7/5. So that's going to be the one solution for x in that equation. And the nice thing about our solution is we can check it. So for any equation that you're solving, you can check your answer by plugging it back in. If you replace each x in that equation with 7/5, then you'll end up with a true statement there. And you can use the calculator to help you with that if you wanted. And fractions are going to be preferred to decimals. So 7/5, for example, is a nice decimal. It's 1.4 exactly, so either answer would be perfectly fine. But let's say your answer was 7/6 instead. We don't want to have to round that decimal and have a less accurate answer. So in general, I don't take the extra step of making the decimal. Just leave it as a fraction. As long as it's reduced, you're good to go. Okay, so that's a linear equation, but I want to focus more on the quadratics because we'll be doing a lot with those in this class. So here, I can use the same techniques. I can isolate my x squared using inverse operations here. So in the same way I wanted to get the x by itself at this step, let me go ahead and get the x squared by itself in this equation. So I'm going to subtract 3 from both sides. That's going to leave me a negative 4x squared equal to 36. And then I can get rid of this multiplication by dividing. So let me divide both sides by negative 4. And that's going to get me x squared equal to 36 divided by negative 4 makes a negative 9. And now that x squared is all by itself, again, inverse operations to solve here, I can get rid of that square by taking the square root of both sides. So the square and the square root cancel just like times 4 and divide 4 cancel. So x is now all by itself equal to, when we take the square root in our solving process, we can't forget to put a plus or minus there. And then when we take the square root of 9, it would be 3. If it's the square root of negative 9, we're looking at 3i. So plus or minus 3i for our two solutions here. And remember, we have two solutions because this is a quadratic and it has a degree of 2. So quadratic equations, two solutions that could be in many different forms. It could be two real solutions, two imaginary solutions. It's always two complex solutions, sometimes just real, sometimes just imaginary, sometimes the real and the imaginaries together, and I think we'll see a variety of those happening as well. All right, another quadratic here. Again, degree of 2 tells me I'm looking for two answers, and I can use a similar strategy. So I'm going to try to get this squared term by itself by dividing both sides by 3. So let me get rid of that division by 3, and hopefully you recognize that 3 can't be multiplied in here because exponents have to happen before multiplication. So instead of multiplying in, which I can't do anyway, I'm going to divide both sides. So that's going to get rid of that and leave me x minus 5, that quantity squared, equal to 54 divided by 3 is going to be, let's see, 3 goes into 5 once with 2 left over, so into 24 8 times, it's 18 there. Now, just like on the previous one, trying to get x by itself, I can use the inverse operations to get rid of both of these things, but this one can't be moved first. Again, this has to go before the parentheses can leave, and we can move that 5. So in this one, we're going to actually take the square root in our next step, and then the square and the square root cancel, leaving me an x minus 5 equal to, on this side, when we solve, we're going to put in our plus or minus, and we're going to have that square root of 18. Now, square root of 18 would be okay, but we want to, in general, have our answers in simplified form. In the same way we would reduce fractions, we're going to simplify radicals. So if I had to simplify radical 18, I'm looking for perfect squares that are in there. So I'm going to use a factor tree to break it down. 18 is 2 times 9, and since 9 is 3 times 3, I know a 3 is going to come out of that radical, and a 2 is going to stay. So it's plus or minus radical 18, but radical 18 simplifies to 3 radical 2. Alright, now remember I'm trying to solve for x here, so I have one more step to take. X is not by itself. There's a minus 5 that I need to move over, so I'm going to add that 3 to both sides. And now x is all alone, equal to, these are not like terms, I can't add this rational with these irrational numbers, so what we're going to get is a set of solutions that looks like this. We're going to have a positive 5 plus or minus 3 radical 2. So these would be our two solutions, 5 plus 3 radical 2 and 5 minus 3 radical 2 would be those two solutions. So those are irrational, just non-repeating, non-terminating decimals if I wanted to get some calculator approximation. But again, exact solutions are going to be preferred to those rounded decimals. So there they are. Not so pretty, but those are the two solutions to that quadratic. All right, here's another where I cannot take the same approach, and hopefully, you're remembering from college algebra why that can't happen. But just look at it here. If I wanted to try to just get this x squared by itself, maybe I tried to do that. Maybe I added the 8x over and then left the plus 4. And then maybe I divided the 5 over, so then I have this 8x plus 4 all divided by 5. But at this point, if I tried to take the square root, then sure, I would have x by itself, but my solution still contains an x in it, which is no good. So that strategy of just isolating the x squared and then taking the square root doesn't always work, which is why we have other strategies. So if we have not only a quadratic term but also a linear term here preventing us from just taking the square root, we're going to try to factor if we can. And if we can't, then we'll try to use the quadratic formula. In my opinion, factoring is easier than quadratic formula. Now, if you don't like factoring, you can go straight to the quadratic formula, but I'm going to attempt to factor this one. So if I'm going to factor this, I need my equation to be, let me zoom out first because this is, okay. I need my equation to be in standard form, so my terms are in order and equal to 0, which means I'm going to subtract that 4 over. So now we're looking good. That's standard form. And I'm going to use the bottoms up method for factoring, but remember, any factoring method is good, whatever works for you. So 5 times negative 4 is negative 20. I'm going to look for factors that add to negative 8, which happen to be negative 10 and positive 2. Once I find those factors, I'm going to divide by my leading coefficient of 5, and then reduce the two fractions I've created if that's possible. So this is going to reduce to negative 2, or just negative 2 over 1, or negative 2, whichever way. The second fraction doesn't reduce, but I'm going to read those fractions from the bottom up to get my factors. So 1x minus 2 is going to be a factor, and then 5x plus 2 is going to be the other factor. And then just a quick check, there's my 5x squared, a positive 2, and negative 10 makes negative 8x, and then negative 4 at the end. So my factoring is good, and now I can easily get my solutions. My solutions are going to be the values of x that make each one of the factors equal 0. Because if I can make a 0 here, 0 times anything would make the whole equation equal 0. And the same thing with the other factor. If I can get a 0 here, then that 0 times anything here is going to make that whole equation equal 0. Now I can see these solutions very easily, but if you need to do some work here, what is it that's going to make x minus 2 equal 0? Well, I would just have to add that 2, and so positive 2 is a solution. And then what is it that's going to make 5x plus 2 equal 0? Well, in this one I would have to subtract 2 and then divide 5, so negative 2/5 would be my second solution. So x equals 2, and x equals negative 2/5. And that's another nice feature of bottoms up, another reason I like to use it, because the opposite of negative 2 is positive 2, and the opposite of 2/5 is negative 2/5. Once I have done my bottoms up process, I can see the solutions. The opposite of these reduced fractions will always end up being those solutions, if that's something that you want to commit to memory. If not, you do not have to. And again, if you don't like factoring, quadratic formula will always work for a quadratic. And so let's try another one. I think this will be another one where we can factor. Again, I'm not going to be able to just get this x squared by itself because I have linear terms along with that quadratic term. So I want to try to factor. So I'm going to put this in standard form, which means I need a 0 where this x is. I'm going to move it over by combining it with its like term. So that's going to leave me a 15x squared. Zoom again. Negative 3 and negative 1 makes negative 4x, and then I have another minus 3, but now equal to 0. And let me see if it factors before I go to the quadratic formula. I just don't like to use the formula if I don't have to. So 15 times negative 3, that's going to be negative 45. Are there factors of negative 45 that make negative 4? There sure are. So negative 9 times 5 adds to negative 4. Negative 9 plus 5 adds to negative 4. Excuse me, and negative 9 times 5 makes negative 45. So I found my factors. I'm going to divide by my leading coefficient, which is 15. I'm going to reduce both of these fractions. This becomes negative 3/5, and this reduces to 1/3. And then read those from the bottom up to get my factors. So 5x minus 3 is a factor. and 3x plus 1 as a factor. And now I can see my solutions. Here, if I was solving for x to make my 0, I would have to add 3, so that'd be a positive 3, and then I'd have to divide 5. And then here, if I was solving for x there, making that binomial equal to 0, I'd have to subtract 1 and then divide 3. So positive 3/5 and negative 1/3 are going to be the two solutions to this quadratic equation. And again, these solutions are the opposites of my reduced fractions here. So the opposite of negative 3/5 is positive 3/5, and the opposite of 1/3, negative 1/3. Okay, so if it's factorable, great. I don't mind factoring, but I'm pretty comfortable with that. So if you don't like it, then you're going to use the quadratic formula, which is what we're going to have to use on this one. So again, I can't just get x squared by itself because I have the quadratic and the linear term here. So if I wanted to try to factor, you're going to see it's not going to work out. 2 times negative 8 makes negative 16. If I was trying to go through factors here, then let's see, I've got 1 and 16 as options, or 2 and 8, or 4 and 4. Now I know I'm going to have to make something negative in there, but I can't get a difference of 3 out of these, or these, or these. So since none of those factors work, factoring not going to be an option. So I can't use factoring here. I'm going to have to use the quadratic formula. Now once again, if you don't like factoring, then the quadratic formula that we review here could also have been used for 4 and 5. But let's do this. I'm going to use the quadratic formula. I have to identify a, b, and c, and I have to remember that formula. Quadratic formula says x is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So we've got our a as our coefficient of x squared, b as our coefficient of x, and c as that constant. If we plug those values into that formula, we're going to get our two solutions to this quadratic equation. So x is going to equal negative 3 goes in for b, plus or minus the square root of, again, 3 in there for b, minus 4 times a is 2, and c is negative 8. And that whole thing is divided by 2 times a, which is 2. So sometimes the hardest part is getting everything plugged in correctly and not missing any signs. So it's a negative 3 plus or minus the square root of, let me try to get one number under the radical here. That 3 squared is going to be 9, and I've got two negatives here, so my product will be positive. 4 times 2 is 8, and 8 times 8 is going to be 64, and 9 plus 64 is going to give me 73 under my radical. And then on the bottom of the fraction, 2 times 2 is going to make 4. Now, I think that's as far as we're going to be able to go on this one, because 73 is not a number we're going to be able to break down. And so this is what our two solutions will look like here. Now, I do want you to be careful. I mean, I can't go through every possible solution, but be careful with this. Let's say you had something like negative 3 plus or minus, I don't know, radical, let's go 18, and let's go another 3 here. If I wanted to divide in this fraction, this 3 cannot go into this 18 because that's in a radical. Now it does divide here, but I can't only divide into one piece of my numerator and then just ignore the other. So if we're going to be able to divide, it's going to have to happen after we simplify the radical. So in this one, 18 is 2 times 9, which means a 3 would come out of that. So you have negative 3 plus or minus, that would be 3 radical 2 divided by 3. Well, now that 3 can divide into, I meant to change colors here, into the 3 here and the coefficient of 3 here, then we can actually do the division. And so negative 1 plus or minus 1 radical 2 would be the simplified form. So if you're going to do any division, the radical would have to be simplified first, and then you can try to divide into the coefficient and that constant that's out in front of the plus or minus. Now, if you had something like negative 3 plus or minus radical 2, if there wasn't if there was just a 1 there already, and then you're trying to divide by 3, again, you can't just divide into one piece here. So I would leave it here, or you could say negative 1 plus or minus 1 radical 2 over 3 like this. Just make sure you're not doing wrong math, okay? Don't divide into radicals, and then don't only divide pieces of the fraction, if that makes sense. I gotta get rid of this because it's looking ugly, not so pretty in my notes here. Okay, so hopefully that makes sense. But again, this is all review, so hopefully we're dusting off the cobwebs, okay? So we got a pretty quick and basic review of solving polynomial equations. Linear should be old hat, quadratic we should see, and hopefully remember all of those different techniques. I don't know that we'll see a lot of cubic, but if we see anything that's cubic or quartic or something that's higher degreed, it's going to be something that we can solve by factoring. Okay, so now let's turn our attention to, whoopsie, I just erased stuff. Turn our attention to another type of equation, which is a rational equation. So a rational equation contains a fraction of polynomials. Hopefully you are already connecting that word rational with the word fraction. So the polynomials we just looked at, if we have those in the top and the bottom, mostly in the bottom, but it could be both. As soon as x is in the denominator of a fraction, we have a fraction of polynomials there, we have this idea of a rational equation. Now, when we have a rational equation, when we have fractions, we have restrictions that we have to be careful with. We know that the bottom of a fraction can't be equal to 0. So if there's some value of x that we could plug in to make the bottom of a fraction equal 0, we have to restrict that as a possibility for a solution, and restrict it as a possible value of x in general. So values of x that make the denominator, that was not a long enough blank, make the denominator equal 0, those have to be restricted. Okay, now I'm going to break this into two types of rational equations that we tend to see, only because if you can recognize one type, it becomes much easier to solve. Sometimes we have proportional relationships and sometimes we don't. If we have a proportional relationship, a proportion, it means it's just one fraction equal to one fraction, just one term on both sides of the equal sign. In that case, we can cross multiply to solve. So this would be an example of a proportion. In a proportion, cross products have to be equal. For instance, if you had a fraction like 5 over 10, we know that fraction reduces to 1/2. Well, if I write that proportion, notice the cross products, so if I cross multiply there I get 10, and the cross products here I get 10 as well, those cross products are equal. It's always true, which is why we can use cross multiplication to solve a proportion. Now, this is a proportion, again, we could solve using cross multiplication, but there are two values of x that we would have to restrict as possible solutions, because there are two different values of x that would make our denominators equal 0. So here, we would say that x cannot equal -3, because -3 and +3 would zero out the bottom of that fraction. And then here we would say x cannot equal +1, because again, if I replaced x with 1, I would have a 0 in the bottom of that fraction. No restrictions for numerators, just denominators can't be 0. Now, if our rational equation is not a proportion, it might look something like this. It could look a whole bunch of different ways, but the key is you're going to have more than just one fraction equal to one fraction. So as soon as you have a second term on either side of the equal sign, it's not a proportional relationship. You've got options, more than what I listed here, but the ones that I tend to work with are, let's either make it a proportion, so you can do the operation here, actually add these two fractions so that it's one fraction equal to one fraction, and then you can cross multiply, or you can use the LCD to clear out the fractions, which is really what I prefer. But whatever you have experience with and are comfortable with. Now, notice in this one too, we have some restrictions. And if you have any denominators that are factorable, you'd want to have those in factored form before trying to find those restrictions. So the difference of squares over there, factoring into x plus 2x minus 2. Now we can see x cannot equal +2. And that same restriction is here. There's no need to say it twice. And also x cannot equal a -2. So while 2 and -2 would have to be restricted as solutions there, those are not defined for those equations. And we have some strategies how to solve, so let's try it. Let's put it into practice. So here, a proportion. Before I solve, I'm going to go ahead and just say what x cannot equal. I know x cannot equal 4, and it cannot equal -1, and I just want to sort of keep that on the back burner there. So I know what x can't be, and I'm going to cross multiply in this proportion to figure out what x can be. So when I multiply here, that 5 is going to have to distribute to the x minus 4, and when I cross multiply here, the 3 again is going to have to distribute to the x plus 1. Those cross products have to be equal. So that's 5x minus 20 on this side, 3x plus 3 on this side, and now we're just solving a linear equation. So I'm going to get my x's together. You can choose to move whichever you want. I'm going to choose the 3 and keep things positive. So 5 minus 3 gives me 2x, and now we're finally ready to solve. So let's get x by itself. If I add 20 to both sides, now I have 2x equal to 23, and then finally divide both sides by 2, and so x is going to be equal to 23 thirds. And there's a nice decimal for that, but again, not necessary to take the step of making that a decimal, since fractions are always going to be precise. Alright, so x equals 23 halves, not one of our restricted values, so nothing to worry about here. There could be cases where your solution ends up being a restricted value. If that's the case, it's not considered a valid solution. It's what we call an extraneous solution. I don't want you to get too hung up on the vocab, but just know that our solution, can't be one of those restricted values. Okay, let's try another. So this doesn't look exactly like the last one. We have one fraction equal to 5. But as long as I have one term on both sides of my equation, I can make a proportion. I can make a fraction out of this 5 by calling it 5 over 1. And we'll do a lot with that. So if you can recognize you have one fraction equal to something you can make a fraction, cross-multiplying is a nice, easy way for us to solve. So 5, before I get ahead of myself, one restricted value, and this one, x cannot equal -4. That would make this denominator equal 0, so let's keep that on the back burner. X can't be -4, but let's cross multiply to figure out what it can be. So 5 has to distribute to the x plus 4, and then multiplying by 1, not going to change the 3x minus 7, but just so you see it. So I have a 5x plus 20 on this side, I have a 3x minus 7 on this side. Again, let me get these x's together. So subtract. Again, I have 2x left. It's looking very similar to the last one. Sorry for the lack of variety in numbers. Okay, let me now solve by getting x by itself. Just solving a linear equation. So I have 2x equal to -27, and then finally divide both sides by 2. So x is going to be equal to -27 halves. And remember, you could always plug this back in to check it. It's not exactly fun. Calculator would help with that, but that -27 over 2, not our restricted value, means valid solution. Okay. Now, here we go with something that I can't just make a proportion. Well, that isn't just a proportion. Again, I've got some options here. It wouldn't be too terrible to make this a proportion. I could, and it wouldn't be too difficult to go ahead and subtract 4 from both sides, and then I would have one value here equal to just one fraction here, and then I have my proportion. But just for practice, I want to show you another technique. I'm allowed to multiply both sides of my equation by the same thing and keep the balance of the equation, right? Like if I'm solving, let's say x divided by 2 equal to 7. I want to get rid of divide 2, so I multiply both sides of my equation by 2, right? Keep the balance of the equation, just like I can add 2 to both sides, multiply 2 to both sides, divide 2 to both sides. If I multiply both sides of my equation by the same thing, then I'm keeping the balance of the equation. Now, when I have fractions in my equation, I'm going to use a very specific thing. I'm going to multiply both sides of my equation by the least common denominator, and that's going to make those fractions go away. So if I'm looking at these denominators, and now there's a whole back lesson on finding common denominators for rational expressions, but if you have each of the components in your denominators, each of those terms, you're going to be fine for getting a common denominator, maybe not necessarily the least, but in this case, the least common denominator is going to include 7 times 1, which is 7, and this factor x minus 2. So if you have each of the factors in your denominators represented in your least common denominator, then you're going to be fine. Now again, it might not be the least, but any common denominator will do. So that is what I'm going to multiply my entire equation by. Both sides of my equation multiplied by 7 times x minus 2, technically over 1. So when I do this here, let me change colors. When I multiply this side by 7 times x minus 2 over 1, and multiply this side by 7 times x minus 2 over 1. Now I'm showing a little more work than I would do myself normally. What happens when I multiply here is the 7's are going to reduce. What happens when I multiply here is nothing reduces because the bottom of my fraction is 1. But when I multiply here, the x minus 2 is going to reduce. Okay, so all my fractions are going to end up going away. Now that looks like a big mess. So let me just take you step by step. And so you can see. So I'm going to multiply here by 7 times x minus, come on, times x minus 2. Again, the 7s are going to reduce, and so I'm going to be left with the 2 and the x minus 2. Bring down my equal. Do the same thing here. Multiply by 7 and x minus 2. Now nothing reduces here, right, because the bottom of my fraction is just a 1. So 4 times 7 is going to make 28 in front of my x minus 2. And then I'm going to do this again one more time here. 7 times x minus 2. Now on this one, x minus 2 is going to cancel. So I'm going to be left with 3 times 7 and my minus. Let's not move that or lose that. So minus 21. And that's it. No more fractions left in my equation. So multiplying every piece of the equation, which is in essence multiplying both sides of the equation, by my common denominator makes all the fractions go away. So now I have a nice linear equation to solve. This will be 2x minus 4 equal to 28x minus 56, and then I still have this minus 21. So that was just distribute here, and I'm going to combine like terms. So 2x minus 4 equals 28x minus, that would be what, 77? And now get my x's together. So I'm going to choose to move these two over. And that leaves me negative 4 equal to 26x, still minus 77. Now I can finally solve. So let me add the 77 over. And now I have 77 minus 4 is going to be 73 equal to 26x. And then lastly, divide both sides by 26. And that's not going to divide in there evenly. So again, this ugly-ish fractional answer, 73 over 26. So there it is, the one solution, which I could plug in to check if I wanted. Now that one solution not restricted, although I forgot to mention, x could not be 2 on this one, right? Not a restricted value, so going to be a valid solution. All right, hopefully I'm not going too fast. I know this is a lot, but let's try one more. Now before I try to figure out what my common denominator is, remember it's got to have all of the components of our denominators. I want to make sure that any of our denominators that are factorable are in factored form. For instance, this x squared minus x minus 6, factors in negative 6 make negative 1, happen to be negative 3 and 2. Dividing by the leading coefficient of 1, we see this factor into x minus 3x plus 2. Which is pretty convenient because that's what we have over here. So that's what our common denominator has to include. It has to have an x minus 3 and an x plus 2. So for my LCD, I'm going to have an x minus 3 and an x plus 2. And then again, just keep on the back burner our restrictions. In this case, x can't be positive 3 and it can't be negative 2, and those same two issues here. So x can't be 3 or negative 2. Alright, now let's multiply every single one of these fractions by that LCD to figure out, or to get the fractions to go away, and let's figure out what x can be. So when I multiply here by x minus 3 and x plus 2, remember that's over 1, so that's going to go away. I'm going to be left with the 3 and the x plus 2. So 3 and x plus 2. When I multiply here by x minus 3 and x plus 2, then the x plus 2's are going to go away, and I'm left with the 5 to be multiplied by the x minus 3. And then when I multiply here by x plus 3, minus 3, and x plus 2, then both binomials cancel, and I'm left with just the 5x. And there we have it. Nice linear equation that we're left to solve. No more fractions. So 3x plus 6 here, a 5x minus 15 here, still a 5x on this side, which means those are going to cancel, but I don't want to lose anybody. So combine like terms, 3x and 5x is 8x. Combine these, negative 15 and positive 6 makes negative 9. I need x's to be together, so I'm going to go ahead and subtract these 8 over. So those are gone, almost there. Let's see, negative 9 now equal to negative 3x, and then dividing both sides by negative 3. I get my solution. Negative 9 divided by negative 3 is positive 3. Now this positive 3 we said up here was not going to be an option for solutions. So if you're solving a rational equation and the only solution you get happens to be something that is restricted, it means that the rational equation doesn't have any valid solutions. So this is what we would call an extraneous solution. So this is called an extraneous solution. And even though it's called a solution, it's not. So this is not a valid solution. So again, if the only solution we had to our equation was restricted, that means the equation has no real solution. So if you were, let's say, taking a quiz or working on your homework and I said, what's the answer? You're going to go, well, there is no solution to this equation. There is no solution to this equation because the one solution that we get had to be restricted because it makes denominators equal 0. Okay, so that can happen. And there are cases, I don't know that we'll see any, I don't know, it can happen. There are cases where you get multiple solutions and maybe you get two solutions and one works and one doesn't, in which case, so like on this one, let's say we had solved and we got x equal to 3 and x equal to 5. Well, 3 doesn't work, but 5 does, so we would keep 5 as the valid solution. So that can happen as well, but if the only solution you get doesn't work, there's no solution to your equation. So you want to make sure you're looking at those restrictions because those aren't possible solutions. Clearing out the fractions, cross-multiplying, an easier approach to recognize when you have a proportion. And yeah, well, we just went through a whole bunch of material, but hopefully it's review. And this again is content that we're going to see come up later in the course. So hopefully this little mini review is good for you. I think you should have enough to get going on your practice, but if you have any questions, feel free to reach out. All right, till next time, take care.